Section 2.4 deals with what we refer to as elementary matrices. Elementary matrices. And what an elementary matrix is something where you take an identity matrix and perform one of the three elementary row operations on it. So remember, our three allowable row operations were swap two rows, multiply a row by a constant or a scalar, or add a multiple of a row to another. So an elementary matrix is a matrix that can be obtained by doing one of these two things. For example, if we want to swap the first two rows, that's an elementary matrix. If we take our identity and double the first row, that's an elementary matrix. If we want to take our second row and add twice the first row to it, then our second row is twice the first row plus the second, twice the first row plus the second, so that represents an elementary matrix. And it turns out that if we have some matrix, if we perform an operation on this, if we want to put this in row echelon form, we need a 0 here. So to get a 0 here, we would do -2 times the first row plus the second row to get our new second row. So of course that would give us 1, 3 on top, -2 times this plus this is 0, -2 times 3, -6, -5. Well, if we represent that with an elementary matrix, we can take that elementary matrix multiply it by our original matrix, and it'll yield us that same thing there. Notice also that I wrote the elementary matrix in front and not on the end. We'll illustrate why that's the case here in a minute, but let's copy this matrix over. And if we're wanting to do -2 twice the first row plus the second row to get our new second row, let's see what elementary matrix is represented by that. So notice we're getting a new second row. So for a 2 by 2 identity matrix, the first row is 1, 0. And let's just jot down the identity matrix that's 2 by 2 for reference. So if we do -2 times the first row plus the second row, that's -2 plus 0. -2 times 0, 0 plus 1 is 1. So this is an elementary matrix that does that particular operation. Now, we have two choices. We can either put this in front or behind our original matrix. And the question is, which side does it need to be on such that we get this to happen? So we're wanting the -2 to be multiplied times the first row, just a 1 times the second row. So let's suppose we put it here. Then to multiply, we do row times column. Notice that would do a 1 times the first column a negative 2 times the second column. We're not wanting the negative 2 times the second column, we're wanting the negative 2 times the first row. Even if we came down here and multiplied, that's doing 2 row times column, 2 times 1, 1 times 2, so that negative 2 each time is being multiplied by that column. And that's not what we're after. So let's go back. And let's take that matrix and let's move it out front. Now let's multiply row and column. So if we do that, we're doing 1 times the 1, 0 times the 2. So 1 plus 0. If we go to the next column, 1 times 3, 0 times 1. So notice our top row didn't change. And notice we weren't changing the top row anyway. Now let's take the negative 2 and 1, do it times the first column. Negative 2 times 1, notice the negative 2 is times the first row. The 1 is times the second row. Negative 2 times 1, that's negative 2, plus 2 is 0. Now when we do this times the next column, negative 2 is times the first row. 1 is times the second row. So negative 2 times 6, or 3 is negative 6, plus 1, so negative 5. Which is the same thing we got here when we did that row operation. So if we're performing a particular row operation, if we represent that row operation by an elementary matrix, we can multiply our matrix on the front side with that, and it yields that change. So if I want to take matrix A and I want to reduce it into a matrix that is row reduced, I'm just going to call that B. So this is just a row reduced version of A. I can multiply A by one elementary matrix that begins, but notice I have to do it out front. If it takes another step to row reduce that matrix, then I take whatever that is, I row reduce, I do one of those 3 row operations again. So my second step would go out front. That yields a more reduced matrix. If I need to reduce it farther, then I multiply what I have so far. I perform another row operation, so I multiply out front again by another elementary matrix to produce another reduction until I have it completely row reduced, however many steps that takes. Or I say row reduced, we could put it completely row reduced, or we could put it in row echelon. So I guess I misspoke. Let's say this is, for now, we'll just say that's row echelon. So this is one thing you'll see. If you want row echelon, multiply A by a series of elementary matrices out front. Now, eventually, if this is an invertible matrix, then think back to when we first found inverses. Let's call, if we were looking for an inverse, we set up an augmented matrix where we put a matrix here that we were wanting to invert. On the other side, we put an inverse matrix, and we row reduced this until A was row reduced to the identity matrix, and whatever we had on the other side was A inverse. Now, we discussed on the first day or in the first section 1.2 that as long as we do one of those three steps, then though that system of equations that results from doing one of these steps is said to be equivalent, or row equivalent to our original matrix. So if we can reduce A all the way down to I, that's said to be an equivalent matrix. So if A can be row reduced down to it, we get to identity. So let's suppose that took 5 steps to do. So we performed one row operation on A, then we performed another one, then another one, then another one, then another one, until that was reduced all the way down to the identity matrix. Then notice, if we were to take both sides of this equation and multiply by A inverse on the right side, notice here, A times A inverse yields the identity matrix. Anything times the identity matrix is itself. So we have this on the right. Anything times the identity matrix is itself here. So we can represent the the inverse of A by the product of the elementary matrices required to take A down to the identity matrix. So that's one thing that we can represent here. Also, we take that same train of thought. To make this shorter, let's suppose it takes 3 steps to get A down to the identity matrix. Then we can represent A as a product of elementary matrices, but not just elementary matrices, but actually the inverse of elementary matrices. Now let's flesh this out real quickly, and then I'll go back and describe what do we mean by the inverse of an elementary matrix. So if we want to solve for A, let's start on the right, or start out front by multiplying by whatever would get rid of this elementary matrix. So to get rid of 1, we multiply it by its inverse. We multiply it on the front side, so multiply on the front side here. So elementary matrix 3 inverse times elementary matrix 3. Those cancel, giving us the identity, but anything times the identity matrix is itself. We want to get rid of E sub 2, multiply by the inverse on the left. So the inverse on the left. So those would cancel. We want to get rid of E sub 1, so the inverse of that elementary matrix. Those cancel. Anything times the identity matrix is itself, so we can drop the identity matrix. So A can be represented as a product of inverse elementary matrices. If we know which elementary operations it takes to reduce A down to the identity matrix, if it can be reduced to the identity matrix, then we can rewrite A as the product of those inverse elementary matrix. Now, just notice, to get A we're multiplying the inverses, and from left to right, they're in increasing order. To get the inverse, we use the regular elementary matrices, but they're in increasing order from right to left instead of left to right. So let's do a couple of things. First of all, let's describe what inverse elementary matrices are. So let's suppose that we take the identity matrix and our new row 2 comes from doubling the old row 2. So we're not getting a new row 1, we're getting a new row 2, and it comes from doubling the old row 2. So if we double this row, we get this. So that's an elementary operation. If we want the inverse of that, then think about what's the inverse of multiplying by 2? The inverse of multiplying by 2 is to divide by 2, or multiply by 1/2. So the inverse elementary matrix of that, instead of multiplying that by 2, divide the second row by 2, so 0, 1/2. And that's multiplying by a scalar. If we want to add a multiple of a row, let's suppose we do 3 times row 1 plus row 2 to get our new row 2, then what that would look like would be we're not changing the first row, but we're doing 3 times the first row plus the second row, 3 times the first row plus the second row to get our new second row. The inverse of that, well, what's the opposite of adding 3? It's subtracting 3. So the inverse of 3 of the first row from R2. So negative 3 times the first row plus the second row, negative 3 times the first row plus the second row. So this would be the inverse of this one. Now our third, or our other row operation, equivalent row operation is to swap row 1 and row 2. So if we swap row 1 with row 2, that looks like, not like that, looks like that. But what's the opposite of swapping row 1 with row 2? Or what would get it back to where it was? Well, if you swap it again, that gets you back to where you started. So that's the inverse, that's the, I'm sorry, sitting here listening to the helicopter fly over my office threw me off. The opposite of flipping row 1 and row 2 would be to flip row 1 and row 2 again. So these are inverse elementary matrices of these. So let's take a matrix. Let's see. Let's do 1, 1, 2, 3. And let's see if that can be written as a product of elementary matrices. So let's begin by seeing what does it take to reduce this down to reduced row echelon, which would be the identity matrix. So let's start out by, we need a 0 here. So negative 2 times the first row plus the second row gives us our new second row. So the first row stays the same. Negative 2 plus 2 is 0. Negative 2 plus 3 is 1. Well, that's handy because we have a 1, a 0 underneath it. We need a 1 here where we have it. So now we need a 0 here. So to get a 0 here, we need to take 1 away. So we're going to do the opposite of row 2 plus row 1 to give us our new row 1. So when we do that, we're not changing the second row, but to get the first row, we do the opposite of this, so 0 plus 1. The opposite of this, negative 1 plus 1 is 0. So that gives us our identity matrix. So let's list our elementary matrices that we did. So our first elementary operation, we didn't change the first row. So if we take our identity matrix, our first row is not changed. Let me write the identity just for reference. But we did negative twice the first row plus the second row. Negative 2 times the first row plus the second row. So that's the elementary matrix that represents that row operation. Then the second elementary operation, we did the opposite of the second row plus the first row. So the opposite of this row plus that row is our new first row. The opposite of this one plus this one is our new first row, and then we're not changing the second row. So that's our E2. So we started with A, we multiplied it, we performed a row operation, so we did this to it, then we did that to it, and after doing those two operations, we ended up with the identity matrix. So a couple things. We could say, well, the inverse of A is whatever we get when we do E2 times E1. Or we could do, what we could do with it is we could say A inverse is A1 inverse times A2 inverse. So let's come up with A inverse to start with. So that takes E2, 1, negative 1, 0, 1, times E1, 1, 0, negative 2, 1. And let's multiply those together. So row times column, so 1, 2, so 3, 0 minus 1, row and column 0, negative 2, 0, 1. Our inverse, so let me just double check. Row times column, 1 plus 2, row times column, 0, negative 1. Row times column, 0, negative 2, row times column, 0, 1. So yes, so that's A inverse if we did everything correctly. Now if we want A, we need to take the inverse of each of our elementary matrices and multiply those out. So we need to list the inverse of each of these. So just a quick reminder, this one we did minus 2 times the first row plus the second row to get the second row. This one we did minus 1 times the second row plus the first row. So the inverse of that first one would be to do plus 2 times the first row plus the second row. So that's the inverse of that. The inverse of this one would be to do plus 1 of the second row, so the second row plus the first row. So if we think about our identity, our second row isn't changing, but if we do our first row plus our second row to get our new first row, we have that. So basically, on this one, the part that's different from the identity is that. So the opposite of that being negative 2 would be to be positive 2. On this one, the part that's not the same as the identity matrix is that. The opposite of that being negative 1 is to be positive 1. So this is the inverse of that. This is the inverse of that. So if we did this correctly, we said A could be represented by A1 inverse times A2 inverse in that order. So 1, 0, 2, 1 times 1, 1, 0, 1. So let's multiply that out and see if that really is A. So row times column, 1 plus 0 is 1. Row times column, 1 plus 0 is 1. Row times column is 2 plus 0, so 2. Row times column, 2 plus 1 is 3. What was A? 1, 1, 2, 3. 1, 1, 2, 3. So that's something we can do with elementary matrices. So quickly, let's talk about some consequences of this. So we said that we can do all these row operations and get down to the identity matrix. Then the inverse is a product of those row operations. But if we cannot reduce A to the identity matrix, if the identity matrix is not able to be arrived at from doing elementary row operations on A, then that means A has no inverse. We already said only square matrices have inverses, so they only will have inverses. A if they're square, and if they can be written as the product, see where I go, of elementary matrices. If you can't write it, A or A inverse, either one as a product of elementary matrices, then it's not invertible. So then we have a list of things that are equivalent. So if we have a square matrix, all of these things are equivalent to each other. We have a list of 5. So the first one is A is invertible. So what is equivalent to saying A is invertible? Well, one thing we've looked at, if we have a system of equations and that has one solution, for each b, then those things are equivalent. Basically, if you were to think about setting up a system of equations in augmented matrix form, if you completely row reduce that, then you'd have the identity on the left, the result on the right. Your resultant vector would be what's on the right in your augmented matrix. If you can get the left side all the way down to an identity matrix, which is reduced row echelon, then A is invertible. The homogeneous system of equation has only the trivial solution. When we talked about the homogeneous system of equations, if you row reduce that and you have a pivot in each row on the left side of your augmented matrix, then that means each of your variables none of them would be free. You have a pivot in each, so none of them would be free. And if you have a pivot in each one, that means you have one solution. Well, if this is homogeneous with one solution, that would be 0, that would be 0, that would be 0. We call that the trivial solution, the 0 vector. Well, if you can row reduce A, has all pivots, row reduce it into an identity, then that's invertible. See, for A is row equivalent to I. And the book says I sub n because they call it A an n by n matrix. N just gives you the size of the identity. It's n dimensional. So if it's a 3 by 3 matrix for A, then this would be a 3 by 3 identity matrix. So if you can reduce A down to the identity using row operations, then we said as long as you can take one matrix, change it into the other with the row operations, they are said to be row equivalent. And lastly, A can be written as a product of elementary matrices. So all of those things are equivalent to each other. Now, one last thing that we do with elementary matrices, and we eventually use this to solve systems of equations, is we do what is called LU factorization. And in LU factorization, L stands for lower. That's a matrix that's lower diagonal. And in a matrix that's lower diagonal, let me make sure I'm telling you this correctly. We have ones down the diagonal, zeros on the upper, and then you can have whatever numbers in the bottom. So for the lower, we have ones down the diagonal. For the U stands for upper, in an upper triangular matrix, is one that doesn't necessarily have to have all ones down the diagonal, but it has zeros on the lower side, non-zeros on the upper side. So if we look at the diagonal, all the non-zero elements are on the upper side here, all the non-zero are on the lower sides here. So if we have a matrix, generally we're going to be looking at ones that are invertible, then we can take a random matrix and write it as a product of a lower and an upper matrix. Let's look at an example of taking a matrix A and let's put it in LU form. Let's do LU factorization. So let's start with matrix A. Let's do 1, 2, 3, 1. So that's our matrix A. And we're going to do row operations on this until we get it into an upper triangular matrix. So we need this to be a 0. So we're going to do minus 3 times the first plus the second to get our new second. So the first row stays the same. If we have a 0, if we have a negative 3 plus 3, that gives us 0. Negative 3, that's negative 6 plus 1, negative 5. So notice that's an upper triangular matrix. You look down the diagonal, everything on that's a non-zero is on the upper side. Now let's express this as an elementary row operation. So that's a 2 by 2 inverse or identity. So this row operation E1, we did the opposite, or minus 3 R1 plus R2. So minus 3 plus 0 minus 3, that's our R2. Minus 3 plus 1, minus 3 times 0, 0 plus 1, so 1. First row we didn't change. So we took our matrix A, we multiplied it out front by E1, and that resulted in this upper matrix. So if we want the lower that goes with it, let's look at getting A by itself. If I want to get A by itself, I multiply out front by the inverse of E1. So those cancel. So the inverse of E1 times U, so this should be our lower. We'll look at E1 inverse. The opposite of doing minus 3 times R1 would be to do positive 3 times R1. So that would be a positive 3 there. So 1, 0, 3, 1. That's our E inverse. Our upper was 1, 2, 0, negative 5. And when you multiply those together, that should give us A. So notice we have a lower times an upper equal to A. Now that wasn't all that impressive because we just did one step. I guess we do need to check, make sure that lower times upper really does give us A. So if we do our row times column, we have 1, 0, so 1. Row times column, so 2 plus 0. Row times column, so 3 plus 0. Row times column, 6 minus 5 is 1. 1, 2, 3, 1. So yeah, this is our LU factorization for A. So let's do that with a 3 by 3. see if we can find one. Let's take 1, 2, 3, 2, 5, 6, 1, 3, 4. So we want to begin by doing the opposite of twice the first row plus the second row to get our new second row. And we're going to call that E1. Then, to make this a 0, we're going to do minus R1 plus R2, that'll be our, plus R3, that'll be our new R3. We'll call that our second operation. So I'm just kind of doing these two together just to save us a little time. So if we do minus 2 plus that, that's 0. Minus 2 times that is minus 4 plus 5 is 1. Minus 6 plus 6 is 0. The opposite of this, that's minus 1 plus 1, minus 2 plus 3, minus 3 plus 4. So now we need a 0 here. So the opposite of row 2 plus row 3, that'll give us our new row 3. So let's call that E3. So first row, same. Second row, the same. The opposite of this one plus that one. So 0, 0, opposite of this plus that is 1. So that gives us our upper. So if this is A, our upper came from taking A and doing our first, then our second, then our third row operation on it. So if we want L, when we move these over, these will be our L. So to get rid of this, we'll do E3 inverse. Then that'll be gone. To get rid of this, E2 inverse. That'll be gone. To get rid of this, E1 inverse. So all of that multiplied together will be L. So let's see. E1 inverse is twice row 1 plus row 2 to get row 2. E2 inverse, that's plus row 1 plus row 3 to get row 3. And E3 inverse, that's plus row 2 plus row 3 to get row 3. So let's take those. See if I can get my tools to come back. Let's take those and put those into matrices. Thinking about 3 by 3 identity matrix being this. So E1 inverse, we're changing the second row. So the first and last row remain the same. So we're doing twice the first row. Then E2 inverse, we're changing the third row, so the first two are the same. We're doing row 1 plus row 3. And then E3 inverse, we're doing row 2 plus row 3. Double check. Yeah. Row 2 plus row 3. So that gives us our new row 3. So row 1 is the same. Row 2 is the same. So row 3 is the sum of these two, 0, 1, 1. So multiplying all those together, that should give us our lower. So let's check. Let's multiply those together. Row and column gives us 1. Row and column gives us 0. Row and column gives us 0. Row and column is 2. Row and column is 1. Row and column is 0. Row and column is 1. Row, column is 0. Row and column is 1. So that's multiplying those two together. Then let's multiply that times the last one. So row times column, 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 here times here, here times here. All right, so that gives us our lower. So we take that lower times upper, that should be equivalent to A. So let's take lower. What was our upper? Our upper was 1, 2, 3, 0, 1, 0, 0, 0, 1, 2, 3, 0, 1, 0, 0, 0, 1. So let's multiply that out and see if that really is A. So row and column, row and column, row and column, row and column, row and column. So that's 4, 5. Row and column, so 6, 0, 0. Row and column, so 1, 0, 0 is 1. 2, 1 is 3 and 0. 3, 0, 1. 3, 0, 1 is 4. So what was A? A was 1, 2, 3, 2, 5, 6, 1, 3, 4. 1, 2, 3, 2, 5, 6, 1, 3, 4. So yeah, we just came up with the proper LU factorization of A. Notice this is lower. This one is upper. So that's doing LU factorization. So real quickly, let's look at one use of LU factorization. We're not going to do a whole lot with it. But let's suppose we have a system of equations that we can write as AX equal B. We talked about what that means. And let's suppose we take A and write it in LU factorization. So we factor A, we write it as LU. So let's make a substitution. Let's let Y be U times X. Now keep in mind, X is what we're looking for. So let's take L, we're replacing U times X with Y, and that equals B. So an example of a system like this, just make up a short example. If this was our lower y1, y2, and we know B is, let's see, this. Then notice this first equation, we multiply row and column, y1, no y2 equals 3. So basically, think about that as a homogeneous, not a homogeneous, augmented matrix. So y1 is 3. 2 y1s, so 6 plus y2 equals 8. Subtract 6 from both sides, so y2 is 2. So that gives us what y is. So this being lower triangular, that makes it easy to solve for y by substituting, taking this value, plugging it in, and so forth, kind of like we did when we did back substitution. So now that we know what y is, u, whatever our upper is, times x, that has to give it, that is the same as y. Y we came out with being 3, 2. U is some upper, just make up example 1, 0, not 0 there, 1, 1, 0, 1. Well, since that's upper, that's easy to solve using back substitution. Keep in mind this is x1, x2. So x2 is 2. x1 plus x2, so x1 plus 2 equals 3, so x1 is 1. So by doing that, you have to solve an intermediate system of equations. But by doing L and U, if those are something you have readily available, then L and U allow you to use back substitution to get y, and then ultimately to get x. So that's 2.4, I would say in a nutshell, a little less than an hour.